Question 16a. A current I flows through loop of wire that lies in the xy plane. Two semicircular arcs shown above have the same center of curvature O. Use Biot-Savart's law to explain why the segment labeled A and B do not contribute to the magnetic field at O. So here in this question you have a loop which is in the form of two semicircular arcs having a center at O. And we need to use Biot-Savart's law to explain why there will be no magnetic field at O because of segment A and B. Now let us first show direction of current through segment A and B. If I follow the current flowing over here, through segment A the current is going to the left, and same with segment B, the current will be to the left. Biot-Savart's law says that I can find magnetic field at any given point by using U0 over 4 pi integral IDL cross r cap over r squared. Now this expression involves a cross product of the current element and the radial direction. And you can rewrite this cross product as mu naught over 4 pi integral IDL sine theta over r squared, because cross product of any two vector can be written as a bar cross b bar to be equal to magnitude of A times magnitude of B into sine of the angle theta between them. Here magnitude of IDL bar you can write as just IDL. R cap is a unit vector, its magnitude is 1 and the angle between them is theta. Now this value of magnetic field depends on the sign of the angle theta between the radius vector and the current element. And sine theta becomes 0 whenever theta is either 0 or 180. That means if the radius vector and the current element both lie on the same line, whether they are going in the same direction or in opposite direction, as long as they are lying on the same line, the angle between them will be either 0 or 180. And in both cases, magnetic field B has to be 0. So let's look at the direction of the current element and radius vector for segment A and B. In case of A, we can draw the radius vector from O to point A. I will call this RA. And for B, from O to point B, we will call this RB. If you noticed in both case A and B, the radius vector and the current lies on the same line. They are either going in the same direction with theta as 0 or they are in opposite direction with theta as 180 degree. And since they both lie on the same line, sine of the angle theta is 0 and hence magnetic field due to segment A and B will be 0. Now this is different from segment C and D. In case of C, the current is going to the right and the radius vector will be going up like this. So here the radius vector and the current element are perpendicular to each other. Same with segment D. So in those two cases, magnetic field will not be 0, but because of A and B, it has to be 0. Next in part B, we need to predict the direction of net magnetic field at point O. Now we already discussed that magnetic field due to segment A and B will be 0. So I just need to find the contribution to magnetic field because of segment C and D. So let us first find the direction of magnetic field at O because of segment C and segment D. So we are going to use the right hand thumb rule. Take the fingers of your right hand and curl them in the same direction as D. So if you curl your fingers in counterclockwise direction, you will notice that your thumb is pointing out. So because of segment D, magnetic field at O will be coming out of the page. So I will write this as B because of D. Coming out is represented by dot and going in will be represented by cross. Now we do the same thing with segment C. We take the fingers of our right hand and curl them in the direction of C, which is clockwise. And when you do that, you notice that your thumb is pointing in. So at point O, because of segment C, the magnetic field is going in. I will write this as B, C. Now these two magnetic fields are opposite in direction. We can find the net magnetic field because of these two as V net to be equal to Vd minus Vc. The net magnetic field has to be a vector sum of these two magnetic field, and when I do vector sum, the vectors coming out of the screen will be taken positive as that is the positive z-axis, and the ones going in will be taken negative. This is why Vd over here is positive and Vc is negative. Now the final direction of net magnetic field will be in the direction of vector which has a larger magnitude. So depending on who has a larger magnitude, we can determine the direction of the net field. Now how do we know who has a larger magnitude? Now we know the expression for magnetic field due to a circular coil at the center. It is B equals mu 0 I over 2R. And since we have only a semicircle, I can find magnetic field due to this semicircular loop by dividing this term by half. So magnetic field for semicircles will be 1 over 2 mu 0 I over 2R. Now this shows that my magnetic field is inversely proportional to the distance r. Inversely proportional means magnetic field will decrease as r increases. So if r is greater, magnetic field for that quantity will be smaller. And if you compare for the two cases over here, we see that the distance for segment C is greater than the distance for segment D. If distance of segment C is greater, that means magnetic field at point O because of segment C must be smaller in magnitude compared to magnetic field due to segment D. If BD is greater than BC, the difference BD minus BC will also be greater than 0. And if it is greater than 0, that means the net magnetic field must go in the positive z direction. It will be in the same direction as BD, as that is the greater vector. So the net direction of magnetic field at point O will be along positive z-axis. So this is how you can predict the direction of magnetic field at any given point. Just compare the magnetic field at that point. Whoever is greater, the net magnetic field will be in that direction.